Let's talk about crystals. You know what they are. Salt on your table, a snowflake on your glove, a diamond. They are all crystals. What makes them a crystal? It's the way their atoms are arranged. They form a repeating pattern. Imagine a perfect grid, like a checkerboard. An atom here, an atom there, another one over there. All in a neat, orderly, predictable pattern. If you move one step to the right, you see the same arrangement. You can map it out. This pattern repeats in space. A crystal has a structure that repeats in space. That's the key idea. For more than a century, that's what a crystal meant. Then, a few years ago, a physicist named Frank Wilczek had a thought. He is a Nobel Prize winner, a very smart guy. He was thinking about this idea of repeating patterns. He thought about space, and then he thought about time. He asked a question. If a pattern can repeat in space, could a pattern repeat in time? Could you have a crystal in the fourth dimension, in time itself? That sounds like science fiction. But it was a serious question. He wasn't talking about a time machine, he was talking about a new kind of matter. He called it a time crystal. So what would that even mean? A normal crystal, like a diamond, just sits there. Its atoms are locked in their repeating pattern in space. They might vibrate a little because of heat, but the structure itself doesn't move. It's static. It's in its lowest energy state. Physicists call this the ground state. Think of a ball that has rolled to the very bottom of a valley. It can't go any lower. It has nowhere else to go. It just stays there. That's a system in its ground state. A perfect diamond at absolute zero temperature is in its ground state. Wilczek's idea was radical. He imagined a system that was also in its ground state, its lowest possible energy state. But instead of sitting still, it would be moving. And not just any movement, it would be moving in a repeating periodic way. Forever. The ball at the bottom of the valley would just keep rolling back and forth on its own without any new energy being added. Its structure would change from one state to another and then back again in a regular rhythm. It would have a pulse. It would be a crystal whose pattern repeats in time. This was a bizarre idea. It seemed to break the known laws of physics. One of the fundamental rules is that a system in its ground state should not be able to move. It has no extra energy to spend on motion. If it moved forever, it would be a kind of perpetual motion machine. Not the kind that creates energy out of nothing, which is definitely impossible, but a different kind, one that moves forever without any energy input or output. This also seemed impossible. So, soon after Wilczek proposed the idea in 2012, other physicists looked at it. They did the math, and they published papers that basically said, sorry, it can't happen. They came up with what's called a no-go theorem. It proved that a true-time crystal, as Wilczek first imagined it, a system in perfect equilibrium and in its ground state, could not exist. The constant ticking would violate the laws of thermodynamics. The universe just doesn't work that way. A ball at the bottom of a valley stays put. A system in its lowest energy state is supposed to be static and, well, boring. For a little while, it seemed like the idea of a time crystal was just a fascinating but flawed thought experiment. A cool idea that just didn't work in the real world, but here's where the story gets really interesting. Physicists are very good at finding loopholes. The no-go theorem was solid. It said you can't have a time crystal in a system at equilibrium. The equilibrium is that state where everything has settled down. A cup of hot coffee left on a table will cool down and reach equilibrium with the room. It stops changing. The no-go theorem applied to systems like that. So, some physicists thought, what about a system that is not in equilibrium? What if you have a system that you are constantly pushing, constantly feeding a little bit of energy? Think about it like this. Don't leave the coffee alone, keep stirring it. Now, it's not in equilibrium anymore. They came up with a new idea, a driven system. Imagine you have a bunch of particles, and you poke them with a laser over and over. Poke, wait a second, poke, wait a second. You are driving the system with a periodic pulse. You are putting energy into it in a regular rhythm. Now, you would expect the system to respond in the same rhythm. If you poke it every second, you expect something inside the system to wiggle every second. You push a child on a swing every time the swing comes back to you. The swing's rhythm matches your push's rhythm. That's the normal, expected behavior. But what if the system did something different? What if you poked it every 1 second, but the system only responded every 2 seconds? Or every 3 seconds, you push the swing every time it comes back, but for some reason it only goes high on every other push. That would be weird. The system would be operating on its own clock, a clock that is slower than the one you are imposing on it. This was the loophole. This is the new definition of a time crystal, the one we can actually build. It's a system that when driven at a certain frequency, responds at a fraction of that frequency. It breaks the symmetry of time. Let's unpack that phrase, breaks the symmetry. It sounds complicated, but the idea is simple. Symmetry just means something looks the same after you do something to it. A perfect sphere has rotational symmetry. You can turn it any way you want, and it still looks like the same sphere. A normal crystal breaks spatial symmetry. Imagine a vast, empty space. Every point in that space is the same as every other point. It has perfect, continuous spatial symmetry. Now you freeze a liquid and make a crystal in that space. The atoms are no longer just anywhere. They are locked into specific spots on a grid. The space is not the same everywhere anymore. It's only the same if you move from one atom to the next identical spot on the grid. The continuous perfect symmetry of empty space has been broken. It has been reduced to a more limited, discrete symmetry. The crystal chose a pattern. A time crystal does the same thing, but for time. The laser pokes create a rhythm in time. Poke, poke, poke. This rhythm has a symmetry. The system is the same at the moment of the first poke, the second poke, the third poke. This is called discrete time translation symmetry. You can jump forward in time by the period of the pokes, and the external force is the same. A normal material would just adopt this rhythm. Its particles would wiggle in sync with the pokes. It would respect the time symmetry you are giving it, but a time crystal does not. It breaks that time symmetry, you poke it and its atoms flip, you poke it again and they flip back. The overall system only returns to its original state after 2 pokes. Its pattern repeats every 2 seconds, even though you are poking it every 1 second. The system has chosen its own longer period. It has broken the time translation symmetry of the drive. This is the mind-bending part. The system isn't just randomly responding, it settles into a new, stable, repeating pattern that has a different period from the force acting on it. And it's robust. It's not a delicate thing. Just like a normal crystal is a stable, solid form of matter, this time crystal is a stable, organized phase of matter. It just happens to be organized in time. So how do you actually build one? It's not easy. You can't just take a rock and shine a laser on it. You need a very specific set of ingredients. First, you need a quantum system. This means you are dealing with the weird rules of the world of atoms and subatomic particles. Things like quantum spin, which is a property of particles that is a bit like them being tiny magnets that can point up or down. Second, you need many of these quantum particles, and they need to be able to interact with each other. A single atom can't form a crystal. You need a community of atoms that can talk to each other and agree on a pattern. Third, you need the drive. That's the periodic poke, like a laser or a microwave pulse that injects energy and sets the tempo. Fourth, and this is a crucial ingredient, you need disorder. This seems counterintuitive. Crystals are all about order, right? But in this case, you need a bit of messiness. Imagine your quantum particles are not all identical. They are in a slightly messy environment. This disorder is important because it prevents the system from just absorbing the energy from the laser pokes and heating up. If it just heated up, it would turn into a hot random soup of particles. The messiness of the disorder helps the particles get stuck in the time crystal pattern. It prevents them from finding an easy way to just turn the laser energy into random thermal motion. This effect is called many-body localization. It's a way of trapping the system so it can't heat up to infinite temperature, which allows the time crystal phase to emerge. In 2016, 2 different teams of scientists, one at the University of Maryland and another at Harvard, announced that they had succeeded. They had built the first time crystals. The Maryland group, led by Chris Monroe, used a line of charged atoms called ytterbium ions. They held about 10 of these ions in a row using electric fields like beads on an invisible string. Each ion has a quantum spin. They used one laser to control the interactions between the ion spins. Then they used another laser to deliver the periodic poke. This second laser pulse would flip all the spins. Here's what they saw. They hit the chain of ions with a laser pulse. The spins flipped. They hit it with a second, identical pulse. The spins flipped back to where they started. The system only returned to its original state after 2 pulses. It was oscillating at half the frequency of the laser drive. They had built a time crystal. It was stable. It kept this sub-harmonic rhythm for many, many cycles. The Harvard group, led by Mikhail Lukin, used a different system. They used a diamond, but not a perfect one. They used a diamond with lots of little impurities in it called nitrogen vacancy centers. These are spots in the diamond's carbon grid where a nitrogen atom is next to an empty spot. Each of these spots acts like a tiny quantum system with a spin. So they had a dense, disordered collection of about 1 million of these quantum spins packed inside a tiny diamond. They used microwaves to poke these spins, and they saw the same thing. The whole system of spins started oscillating together, but at a frequency that was a fraction of the microwave drive frequency. It was another clear signature of a time crystal. The fact that two different teams using completely different physical systems saw the same fundamental behavior was a huge confirmation. Time crystals were real. They were not just a theoretical curiosity anymore. A new phase of matter had been created in the lab. So what does this all mean? Why is this important? It's not just a cool physics trick. The discovery of a new phase of matter is always a big deal. It expands our understanding of what is possible in the universe. We used to think of phases of matter as solid, liquid, gas, and plasma. Then, we found more exotic ones like superfluids and Bose-Einstein condensates. A time crystal is a new entry on that list. It's the first one that is a non-equilibrium phase. It can only exist when it is constantly being fed energy. This opens up a whole new frontier of physics, the study of how matter can organize itself under such conditions. But there are also potential practical applications down the road. They are still very far off, but the ideas are exciting. One of the biggest areas of interest is quantum computing. A quantum computer uses quantum bits, or qubits, to do its calculations. These qubits are incredibly powerful, but also incredibly fragile. The slightest disturbance from the outside world, a little bit of heat, or a stray magnetic field can mess them up and destroy the calculation. This problem is called decoherence. It's the biggest challenge in building a useful quantum computer. Time crystals are, by their very nature, surprisingly robust. The interactions and disorder that create the time crystal phase also protect it from small errors. The collective pattern is very stable. If you try to flip just one spin in the time crystal, the interactions with its neighbors will tend to flip it back. The whole system works together to maintain its special rhythm. This inherent stability could be very useful. Scientists are exploring if the principles behind time crystals could be used to build more stable qubits, or a kind of quantum memory that is much more resistant to decoherence. The time crystal's persistent protected oscillation could act as a stable carrier of quantum information. Another potential area is in ultra-precise measurement. Because a time crystal has an extremely stable and predictable internal clock, it could form the basis for incredibly accurate sensors. For example, they could be used to build sensors that can detect tiny changes in magnetic fields with unprecedented precision. Any tiny change in the environment would slightly alter the rhythm of the time crystal, and we could measure that alteration. But for now, the main importance is fundamental. We have discovered that matter can be organized in a way we never thought possible. For all of history, we organize the world around us in 3 spatial dimensions. A crystal was a map of order in space. Now we know that order can exist in the 4th dimension, time. It forces us to rethink some of our most basic ideas about what a phase of matter even is. It's also important to be clear about what a time crystal is not. The name is very evocative and can be misleading. It has nothing to do with time travel. It doesn't freeze time or let you move through it. It is a piece of matter, not a machine from a movie. It is also not a perpetual motion machine that generates free energy. This is a common point of confusion. A time crystal needs a constant input of energy from the outside, from the laser or microwave drive, to keep going. If you turn off the drive, the time crystal stops ticking and the special order disappears. It doesn't violate the law of conservation of energy. It takes in energy from the drive and uses it to maintain its ordered motion, eventually dissipating that energy as heat. What makes it special is how it organizes that motion, in a stable rhythm that is different from the rhythm of the drive. So, is it just a fancy clock? Not exactly. A clock is a device we build to measure the passage of time. A time crystal is a phase of matter whose very structure is a repeating pattern in time. It's as if the clockwork is built into the fundamental fabric of the material itself. Its ticking is an inherent property of its collective state. The field is still very new. Scientists are now working on creating many different kinds of time crystals. The first ones were called discrete time crystals because they responded to a pulsed drive. Now, researchers have created continuous time crystals that are driven by a continuous laser beam instead of pulses. They are trying to make them bigger, with more particles. They are trying to make them last longer. They are studying how 2 time crystals might interact with each other. There is even speculation, and this is just speculation, that the principles of time crystals might show up in other areas of physics, even in cosmology. The universe is a dynamic, evolving place full of things that are not in equilibrium. It's possible that this kind of temporal order could exist in other, more exotic systems that we haven't discovered yet. The journey of the time crystal is a perfect example of how science works. It started with a bold, almost crazy theoretical idea. That idea was then seemingly shot down by a rigorous mathematical proof. But then, a clever loophole was found, redefining the idea in a way that was possible. Finally, experimentalists with incredible ingenuity managed to build it in their labs, turning science fiction into scientific fact. What we are left with is a profound and beautiful concept. A crystal is a breakdown of symmetry in space. It trades the perfect uniform symmetry of a liquid for a more structured, patterned, and in some ways more complex, solid form. A time crystal shows that matter can do the same thing with time. It can spontaneously break the symmetry of a continuous flowing river of time and settle into a discrete rhythmic pulse. It's matter with its own internal heartbeat. It's a completely new way for the universe to be organized, a dance of atoms choreographed not just in space but across the measure of time itself. The discovery has opened a door, and we are only just beginning to peek through it to see what other strange and wonderful forms of matter might be waiting for us. It challenges our intuition and reminds us that the universe is still full of surprises.